Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. Also, if you find my videos interesting and important to your studies, please don't forget to subscribe. Uh, that's the one way. That's one way you can help me promote my channel to keep me going, inspired and refreshed. Problem 25. Determine y such that the hydrostatic force above the red line on the plate is equal to the hydrostatic force below this red line, below this line on the plate. So here's the given figure. The condition is the hydrostatic force above the red line is equal to the hydrostatic force below the red line. So for the solution, let's locate the centroid of area of each. So that's GU. And therefore, because this is 2 plus 6, 8, and that is y, so this is 8 minus y. This is equal to y minus 2, this one. And this is the centroid of the lower part below the red line. And the distance to the liquid surface is denoted by HGL. So this is HGU, and this distance is HGL. Let's read it from this figure here. So F upper equals F lower, that's the condition here. And force is gamma Hg times area. So gamma times HGU times area U equals gamma times Hg lower times area L, area lower. So cancel out gamma. HGU is equal to, from the figure, y minus half of y minus 2, while the area of the upper part is 3 meters times y minus 2. So y minus y over 2 times 3 times y minus 2 equals HGL is equal to 8 meters, that's 8 up to the bottom, then minus half of 8 minus y, because the area is rectangular, so the distance to the centroid is half of the height. So 8 minus y over 2, and the area is 3 times 8 minus y as shown. So cancel out 3 and simplify this into y minus y over 2, or y over 2 plus y over 2 plus 1. Negative of negative 2 over 2 is plus 1. Then times y minus 2. Then here with 8 minus 8 over 2 is 4 plus y over 2. Then 8 minus y. So y over 2 plus 1 times y minus 2 equals 4 plus y over 2 times 8 minus y. Simplifying, this is y plus 2 over 2 times y minus 2 equals 8 plus y over 2 times 8 minus y. Cancel out 2. This is y plus 2, y minus 2, so that's y squared minus 4. And this is 8 plus y, 8 minus y is 64, 8 squared 64 minus y squared. So y squared minus 4 equals 64 minus y squared. 2y squared equals 68. So y squared equals 34. Therefore, y is square root of 34, or in decimal, it is 5.831 meters. Problem 26. Each of the two gates has a constant width 2.4 meters perpendicular to the paper or screen. Calculate the force P required to maintain each gate in the position shown. Consider the liquid as water with B 1.8 meters, H 2.7 meters, radius 1.5 meters for the second gate, and neglect the weights of the gates. Then if the weight of the gate in parts A and B were considered, what would be the value of P? The gate is made of steel, specific gravity 7.86, 25 millimeters thick. Now for the figure shown, here is the gate. We will call the width perpendicular to the screen or paper as W in this case. So I'll use pressure distribution instead of gamma Bardade's area formula because we have composite gate here. So this is the pressure diagram on the vertical projection of this gate, Hatch gate. So this is gamma of water times H, pressure here, and the distance of F, which is horizontal, is H over 3 from the bottom. Because the pressure distribution is triangular, this is exposed to the atmosphere. Let's divide this trapezoidal section into two parts, rectangular and triangular, as shown, so that we can compute the weight of water on this rectangular part. Let's call that WR. Its distance from the vertical line through A is half of B, of course. And we have W triangle. This is B over 3. So summation of moment about A equals 0. Let's establish the equation. P times H equals F times H over 3 plus WR times B over 2 plus WT times B over 3. So that's the working equation. F is volume of pressure diagram, so 1/2 of gamma H times height H perpendicular to the board W. So area of triangle 1/2 gamma H times H, and width perpendicular to the board W, so that's the volume, and it represents this force here, volume of pressure diagram. So simplifying, that's 0.5 gamma of water, W H squared, where W is 2.4, H is 2.7. Then for WR, it is equal to gamma of water times area B times width perpendicular to the board W. So gamma of water times volume of water, which is area of the rectangle B by B, which is square, times width perpendicular to the board W. So simplifying, that's gamma of water WB square, where W is 2.4, B is 1.8 meters. Then for the triangular, weight of the triangle is gamma of water times 1/2 of B times quantity H minus B. The height of this triangle is H minus B. Then width perpendicular to the board W. Simplifying, that's 0.5 of gamma of water times B, WB times H minus B. Computing for F, 0.5 times 9.81 times 2.4 times 2.7 square. So F is 85.818 kilonewtons. WR is 9.81 times 2.4 times 1.8 square, 76.283 kilonewtons. WT is 0.5 times 9.81 times 2.4 times 1.8 times 2.7 minus 1.8. So that's 19.071 kilonewtons. Substitute in this formula here. P times 2.7 equals 85.818 times 2.7 over 3 plus 76.283 times 1.8 over 2 plus 19.071 times 1.8 over 3. Then we can now solve for P. P is equal to 58.27 kilonewtons. Considering the weight, so call this weight 1, and take note that B is from vertical line through A to centroid of this gate. So we neglect the thickness here because it passes through the centroid, and the leveling of B is through the centroid. So the moment arm is still B for W1. And this one, W2, the moment arm is half of B, midpoint of this inclined line or cross-section of the gate. So weight 1 is 7.86 times 9.81. Volume of this portion of the gate is B, which is 1.8, perpendicular to the board 2.4, thickness of gate 0.025. So 1.8 times perpendicular to the board 2.4, so that's the area of the rectangular part, times thickness, so that makes it volume 0.025, so 8.3275 kilonewtons. While for weight 2 is 7.86 times 9.81, specific weight of steel times volume of this gate, which is the inclined length of this gate, square root of b square plus 0.9 square, h minus b is 0.9, then times 2.4 perpendicular to the board times thickness 0.025. So A2 is 7.86 times 9.81, square root of 1.8 square plus 0.9 square times 2.4 times 0.025. That's the volume of this gate here. So 9.3104 kilonewtons. So summation of moment about A equals 0. So P prime times 2.7 equals 85.818 times 2.7 over 3 plus 76.283 times 1.8 over 2 plus 19.071 times 1.8 over 3 plus weight 1 8.3275 times B 8.3275 times 1.8 plus 9.3104 times B over 2 or 1.8 over 2. So solving for P prime, considering the weight of gate, 66.93 kilonewtons. Then in the second part, so for the horizontal force, the radius is denoted by R. So this is the pressure diagram. The pressure here at A is gamma of water times R because the height is R. Then let's have FB, and this distance is R over 3. R over 3. This is WB, weight of water, inside this quarter circular section. And that distance is 4R over 3 pi, but we don't worry about that because by principle, the resultant of the horizontal force and vertical force on this circular gate by principle passes through the center of the circular gate here. So by principle of transmissibility of a force, we can move the resultant along its line of action at the center here, or we can move the components of the resultant here by principle of transmissibility. So the reaction is denoted by RA, and we delete FB, replace and WB, and transfer them here. So we have FB and WB, so that only FB will have moment about A. WB passes through A. So if we sum up moment about A, disregarding the weight of the gate first, so we have FB times R equals P times R also. So that means FB equals P. Cancel R. So P equals FB, and FB is volume of pressure diagram, 1/2 of gamma of water R times height R times width perpendicular to the board W. So it is 0.5 gamma of water W R square. W is 2.4, R is 1.5, and gamma of water 9.81. So P therefore is 0.5 times 9.81 times 2.4 times 1.5 square. So P is 26.49 kilonewtons. For the second part, let's have the weight of the gate, and it acts here. Remember, the centroid of this arc is centroidal area of the arc, which is 2R over pi from the center. Either way, so that's 2R over pi. And everything is known. So weight of gate is the length of this arc times width perpendicular to the board, that's the surface area, times the thickness 0.025. The length of this arc, because this is quarter circular arc, is pi r over 2. Because the circumference of the whole circle is 2 pi r, then divide it by 4, so pi r over 2 times width 2.4 times thickness 0.025. So weight of gate is 7.86 times 9.81, then the specific weight of steel, then the volume is pi r over 2 as mentioned earlier, times width perpendicular to the board 2.4, that's the surface area, times thickness 0.025. So weight of gate is 10.901 kilonewtons. Summation of moment about A equals 0. So we have P prime times R equals P FB times R plus WG times 2R over pi. Substituting, FB is equal to 26.49 in part A. So P prime times 1.5 equals 26.49 times 1.5 plus 10.901 times 2 times 1.5 over pi. So solving for P prime, considering the weight of the gate, 33.43 kilonewtons. Problem 27. For the gate shown, determine the force P required to hold the gate in place. So here is the given figure. And for the solution, we have F here, center of pressure is there. This is the centroid of area. And the distance to the base is 4r over 3 pi. Call this E sub V. And this is also the centroid G of the semicircular section. This distance is 4r over 3 pi. Remember the location of centroid. Then, therefore, the distance from G to the water surface is 1.5 plus 1.8, 3.3 minus 4r over 3 pi. And that is equal to 2.536 meters. Again, that 2.536 is 1.5 plus 1.8. So 3.3 minus 4r over 3 pi. So 2.536 meters. So F is pressure at G times area of the gate. Pressure of G times area. Where the pressure at G is negative 10 plus specific weight of water 9.81 times 2.536. So negative 10 plus 9.81 times 2.536, and that is equal to 14.87 78 kilopascals, then equated to specific weight of water in contact with the gate times Hg, so that we can solve for Hg. So solving for Hg is 1.5166 meters. The other way of computing Hg is you convert pressure head negative 10 into pressure head of water, negative 10 over 9.81, then you add 2.536 and you will get 1.5166 also. So E sub V equals 0.1098 r to the fourth over area 0.5 pi r square times Hg. Area is pi over 2 radius square, area of semicircle. And the moment of inertia with respect to the centroidal axis parallel to the diameter is 0.1098 r to the fourth. So remember that. So simplifying, it is 0.0699 r square over Hg after we cancel r square, and 0.1098 divided by 0.5 pi. So substitute 0.0699 r is 1.8. This one, that's the radius. 1.8 square over Hg 1.5166. So E sub V is 0.1493 meter. Having found E sub V, we can now sum up moments about A equals 0. So P times 1.8 equals F. The moment arm of F is 4r over 3 pi minus E sub V, where F is pressure at centroid times area. So let's solve it first. 14.878 times area pi over 2, 1.8 square area of semicircle. So F is 75.72 kilonewtons. So summation moment A equals 0. P times 1.8 equals F times 4r over 3 pi, 4 times 1.8 over 3 pi, minus 0.1493 E sub V. So from there, we can solve for P. P is equal to 25.86 kilonewtons. Problem 28. The cross-section of a freshwater tank with a slanted bottom is shown. A rectangular door, 1.6 meters by 0.8 meters, which is perpendicular to the plane of the figure, 0.8 meter wide. In the bottom of the tank is hinged at A and is opened against the pressure of the water by the cable under a tension P as shown. So calculate P. By the way, I also solved this in statics, problem 52 on distributed forces under the topic hydrostatic pressure. So you look at the solution there, it's different from my solution here, and I use pressure diagram there because in statics we have distributed forces. So just look at the solution. Anyway, the answers are the same. So for the solution, let's locate the centroid. That's the centroid of area. And the vertical distance to the liquid surface is denoted by hg. And because the length or height of the gate is 1.6, that g there from A is half of 1.6.8. And since this is inclined 30 degrees, so this vertical distance from G to this A here is 0.8 sine of 30, which is 0.4. So that hg is 1.2 plus 0.4, 1.6. So this is F, and it acts at the center of pressure. And the distance is denoted by E from the figure. So F is gamma of water hg times area of the gate. Area of the gate is 1.6 times perpendicular to the board 0.8. So F is hg is 1.2 plus 0.8 sine of 30 as mentioned earlier. So it is 1.6 meters. So substitute. F is 9.81 times 1.6. The area is 1.6 times 0.8. So F is equal to 20.091 kilonewtons. Then for E, HR square sine of theta over 12 hg, where HR is 1.6, theta is 30 degrees, hg is 1.6. So E is 1.6 square sine of 30 degrees over 12 times 1.6. So E is equal to 1 over 15 meters. Then summation of moments about A equals 0. P, the moment arm of P is 1.6 cosine of 30. This horizontal projection of the gate, 1.6 cosine 30, equals F, the moment arm of F is 0.8 plus E. 0.8 A to G, 0.8 plus E, which is 1 over 15. So P times 1.6 cosine 30 degrees equals F, 20.091 times 0.8 plus E, 1 over 15. Solving for P, P is equal to 12.57 kilonewtons. Problem 29. A vat of oil with specific gravity 0.86 has the vertical end section shown below. The end sections are 3.6 meters normal to the paper or screen. Determine the following. The hydrostatic force on one end ABCD, the moments of the hydrostatic force in part A about the bottom BC and about the vertical end AB, and the hydrostatic force on the slanted end CD. So here is the given figure. So let's divide the area into two parts, rectangle and triangle. Remember, this is an end section. So that's it. So the rectangle is a square, 1.5 by 1.5, and the triangular section is 2.4 minus 1.5, 0.9 meter by 1.5 meter. So this is the centroid of the rectangular section. Its distance to the free oil surface is half of 1.5 0.75. So that 0.75 meter is already HGR, or barred H of the rectangle. Then for the triangle here, its distance from the top, this is G sub triangle, its distance from the top is 1/3 of 1.5, so 0.5, and that 0.5 is already barred H of rectangle, or HGT, 0.5 meter. Then the location of the forces would be below at the distance E, center of pressure of rectangle, and this is the center of pressure of triangle. And if we draw a line through the center of pressure of triangle and the length is x1, remember that by principle, the force due to triangle, the force due to the hydrostatic force on this triangular section is at midpoint of x1 or x1 over 2 from either the left or the right. So remember that principle. You look at the explanation and the derivation, why it is that reason or result or explanation. So to have a picture of the end view, let us say this is the vertical end, which consists of rectangle and triangle. Let's transfer everything here. So this is the centroid of the rectangular part, and this is the center of pressure of the rectangular part where F of rectangle acts. So that's why you have F of rectangle, and that distance is EVR. That distance is EVR. Then centroid of triangle, G of triangle, so that's 0.5 already indicated here. Center of pressure of triangle. Then this is E sub VT, the vertical distance. And at CPT acts F of triangle. So F is gamma HG area or gamma Barditz area. For rectangle, gamma of oil 0.86 times 9.81, HG is 0.75, and the area of rectangle is 1.5 by 1.5. So F of rectangle is 0.86 times 9.81 times 0.75, area 1.5 by 1.5. So FR is equal to 14.237 kilonewtons. F of triangle is equal to gamma 0.86 times 9.81 times barred H of or HG of triangle 0.5, area 1/2 of 0.9 by 1.5. So F of triangle is equal to 2.847 kilonewtons. So we can now answer the first part, F on the end panel, FR plus FT. But before that, let's have AVR, which is height of rectangle square over 12 HG of rectangle. There's no sine theta because the plane or the surface is vertical. Sine of 90 is 1 anyway. So height of rectangle is 1.5 square over 12 times 0.75. So although it is anticipated 2/3 of CPR is 1/3 of 1.5 or 0.5 from the bottom, because the pressure diagram on the rectangular area is triangular. So 1/3 from the bottom, and that is 1/3 of 1.5, 0.5. But anyway, we can show here that it is still 0.5 after solving for EVR, because this gives us a value of 0.25 meters. So 0.75 plus 0.25 is 1. So that means 1 from the top, 0.5 from the bottom. So therefore this distance is 0.5. This 0.5 here is 0.75, GR to bottom 0.75, half of 1.5, minus EVR, which is 0.25. That's why that's 0.5. Or in short, 1/3 of 1.5, because the surface of oil is exposed to the atmosphere. As I said, the pressure distribution on that rectangular area is triangular. So the line of action of FR is 1/3 of the height of the rectangle, or 1/3 of the height of the pressure distribution, which is triangular. So AVT is HT square over 18 HGT. So HT is also 1.5 square over 18, and HGT is 0.5 meter. So the result is it's also 0.25 meter. So 0.5 plus 0.25 is 0.75. Therefore, that 0.75 is half of 1.5. So therefore, XC1, because CPT is exactly half of the overall height of the triangle, then X1 is also half of this length, which is 0.9. So if that is 0.9, x1 is half of 0.9. So 0.45 meter. The general way is apply similar triangles. X1 as to 0.75 equals 0.9 as to 1.5. You will get that. It just happens that the center of pressure of the triangular part is 0.75 meter below the oil surface, or 0.75 meter above the bottom. Or in short, that's the point which divides the height exactly into halves. So that's why it's 0.45 here. So F therefore can now be solved. It is FR plus FT. That's the question to number 1. 14.237 FR plus FT 2.847. So F is 17.08 kilonewtons to 4 significant figures. The moments of the hydrostatic force in part A about the bottom BC. So there is already moment arm for FR, which is 0.5 from the bottom. The moment arm of FT from the bottom is 0.75, as mentioned earlier, because this is 0.25. 0.5 plus 0.25 is 0.75. So it's the distance of FT, which acts here at the CPT to the bottom, is 0.75. So moment about bottom, which is BC, is FR 14.237 times 0.5 plus FT 2.847 times 0.75. And it is equal to 9.254 kilonewton meter. Then moment about vertical distance AB is FR. Of course, this distance, because this is rectangular, half of 1.5 is 0.75, plus FT. The moment arm of FT from AB is 1.5 plus x1 over 2 by principle. So MAB equals 14.237 FR times 0.75, half of 1.5, plus FT 2.847 times quantity 1.5 plus x1 over 2 plus 0.45 over 2. So moment about AB is equal to 15.59 kilonewton meter to 4 significant figure. Then the hydrostatic force on the slanted side CD, remember this is rectangular, it just happens that it is inclined. The length of this is square root of 0.9 square plus 1.5 square, and the width perpendicular to the board is 3.6 as mentioned here. So Fs is gamma HS area, where HGS area, where HGS is equal to, because this is straight line, is 0.75, half of 1.5. The distance from liquid surface to centroid of this inclined face is still half of 1.5, so 0.75 HGS. Area S is length of this CD, square root of 0.9 square plus 1.5 square, times width perpendicular to the board, as I said, 3.6. So Fs is 0.86 times 9.81 times 0.75 times square root of 0.9 square plus 1.5 square, length times width perpendicular to the board, 3.6. So Fs is equal to 39.85 kilonewtons. So that's it for this problem 29. Problem 30. Locate the distance y of the red line from the vertex of an isosceles triangle plate such that the hydrostatic force above this red line on the plate is equal to the hydrostatic force below this line on the plate. So here is the given figure, and the condition is the hydrostatic force on the portion above the red line is equal to the hydrostatic force below this red line. So meaning to say, the hydrostatic force above and below would be equal, such that the hydrostatic force of the entire triangular plate is, if we denote that as F, then the hydrostatic force above the red line is 1/2 of that total hydrostatic force. So that's the idea and the analysis. So Fu is 1/2 of F, F is the total hydrostatic force on this uh, whole triangular plate, and it is equal to specific weight, barred H area, where barred H is 1 plus, of course, 2/3 of 5, and the area is 1/2 of 3 times 5. So Fu is 1/2 of specific weight, 1 plus 2/3 of 5 times 1/2 of 3 times 5. So this is the area of the whole triangle. This is barred H1 plus 2/3 of 5 to locate the centroid of the entire triangle. Then times specific weight. Then half of that would be the force on the upper part. So computing, Fu is equal to 16.25 of specific weight of the liquid. Then we solve for Fu in terms of Y. Let's locate the centroid. That's the centroid. Then the distance to the liquid surface is the distance of the centroid, HGU. So HGU is 1 plus, of course, this distance in terms of Y is 2/3 of Y. And let's call this dimension X, that one, so that Fu is also specific weight, then 1 plus 2/3 of Y times 1/2 of X times Y, the area. Simplifying, Fu equals gamma quantity 3 plus 2Y over 6 times xy. Then by similar triangles, x as to y equals 3 as to 5. So that x is 0.6 of Fy. So gamma over 6 times 3 plus 2y times x, which is from here 3/5 of y, or 0.6 of y times y. So Fu is 0.1 of specific weight, y square, quantity 3 plus 2y. And substitute the value of Fu, which is 16.25 of specific weight. So 0.1 specific weight, y squared 3 plus 2y. Cancel out specific weight. So 16.25 equals 0.3 y squared plus 0.2 y cubed. So rearranging, 0.2 y cubed plus 0.3 y squared minus 16.25 equals 0. And then using your high-tech calculator, the calculator is allowed to use cubic equation like this, and the only positive root is equal to 3.885 meters. The other two roots are complex conjugates. So y is 3.885 meters. Problem 31. For the rectangular gate shown, determine the force P required to open the gate. Part A, by neglecting the weight of the gate, and Part B, considering the weight of the gate, which is made of steel of specific gravity 7.86 and 25 mm thick. So here is the given figure. So it's solving for the force F. We use pressure at the centroid times area here because we have a complicated situation, not so complicated, as long as you are expert in the principle on hydrostatic pressure. So the location of the centroid is, because the length or height of the gate is 6, so from B or from A, 3 meters, half of 6. So this is the force F, and it is below the centroid. It is acting at the center of pressure. So this is the centroid of the gate. So this is 3 meters. Distance between the centroid and the point where F passes is E, and we call that G, the centroid of the gate. Center of pressure C sub B, and the distance between them along the plate is E, and from B to G 3 meters as shown. So working equation, summation moment about the hinge equals 0. When the gate is about to open, there will be no reaction at A. So P times 6 meters cosine 60, then equals F. The moment arm of F from B is 3 plus E. So F is pressure at G times area of the gate. The pressure at G is beginning with this point here is 10 plus 10 plus 0.92 times 9.81 specific weight of oil times 2. Then plus we go down farther by, this is water, 1.5 plus this vertical distance to point G is 3 sine 60. So plus 9.81 times quantity 1.5 plus 3 sine of 60 degrees. So computing for pressure at G, it is equal to 68.253 kilopascals, and it is equated to specific weight of water times Hg, so that we can compute the equivalent distance of the centroid of area to the point where water is exposed to zero pressure. So everything is converted to water to the point where pressure is zero. So solving for Hg is 6.9574 meters. To get 6.9574 meters in another way, then convert 10 into pressure head of water. So do this, use your calculator. 10 divided by 9.81, 10 kilopascals divided by 9.81, then plus 0.92 times 2 divided by 1, so it's still 0.92 times 2, then plus 1.5 plus 3 sine of 60. 10 divided by 9.81 plus 0.92 times 2 plus 1.5 plus 3 sine of 60 degrees. You will get the same answer. So again, 10 divided by 9.81 plus 0.92 times 2 plus 1.5 plus 3 sine of 60 degrees. So you will get 6.9574 meters. So that's Hg. The distance from G, vertical distance from G to the point where the system is replaced by water, pure water, and to the water surface where it is exposed to zero pressure. So having found this, we can now solve for F. Pressure at the centroid 68.253 times area. So 68.253 area 2 times 6, area of the rectangular plate. So F is 819.036 kilonewtons. Then let's solve for E. E is height of rectangle square sine of theta divided by 12 Hg. So height of rectangle is 6, so 6 square sine of 60 degrees over 12, quantity 12 times 6.9574. Solving for E is 0.3734 meters. Then summation moment about the hinge equals 0. So part A, P times 6 cosine 60 degrees equals F, which is 819.036. The moment arm is 3 plus E, 3 plus 0.3734. From there, we can solve for P. P is 921.0 kilonewtons. Then in part B, let's consider the weight of the gate, and it acts at the center of gravity of the gate, or in this case, centroid also. And the moment arm of W is 3 cosine of 60. So this is 3 cosine 60. And it is same sense as the moment of F about the hinge, counterclockwise. So it's in the right side of the equation also. So weight equals specific weight of steel. So this is the equation. P times 6 cosine 60 degrees equals F times 3 plus 0.3734 plus W times W times 3 cosine of 60 degrees. So solving for W, that's our working equation. W is specific weight of steel, 7.869.21, volume of steel, area of the gate times thickness of the gate. So 2 times 6 times 0.025. So W equals 23.132 kilonewtons. Then substitute into this equation. P times 6 cosine 60 degrees equals 819.036 times 3.3734 plus 23.132 times quantity 3 cosine of 60 degrees. So computing the value of P considering the weight of gate is 932.5 kilonewtons. So that's it for this problem.